Right. So in this video, I will try to answer some questions that would be applying some of the concepts you guys have just watched in the previous video. So here's an IB question that's asking the following. The graph below shows the variation with time of the displacement x of the waves emitted by S and L. So this is wave S and this is wave L. First things first, we need to understand our graph. This is the displacement time axis from equilibrium, and this is a time axis. Sorry, this is the displacement axis, this is the time axis. And of course, from this graph, we're only able to deduce the time period because this is given to us in time. If you had this given to you in distance or displacement, you'll be able to determine the wavelength. Right, but that's not the purpose of this video. So now, the question is, deduce the relationship between the phase of L and the phase of L. So they're asking you for the phase difference. Right, so you guys already watched the prior video. Now, in order to answer this question, again, we're going to try to compare this to a unit circle, right? So if you look at this graph, or this wave, this is wave S. Wave S at a given time, right? We're going to freeze time at this moment. At a given time, at this time, wave S has attained 90 degrees, but wave L is yet to attain 90 degrees, which it does later on, all right? So that means from this, we can clearly see that wave S is leading in front of, or leading ahead of wave L, all right? So we've answered part of the question. So now we can tell that wave S is leading ahead of wave L, but another question in order to make this answer complete is, by how much is wave S leading wave L? In order to answer this question, we need to know the difference in the time, right? How much time is wave S using to lead wave L, and how does that compare when we want to convert that to degrees, or to our degrees or radians, or whichever unit of circle angle we're using for the circle. So if you look at this wave again, the two waves, so wave S is leading wave L. When wave S attains 90 degrees, it takes some time for wave L to attain that 90 degrees, right? So that already gives you the answer, right? So you have a difference in time here. Another way to look at it is wave S attains 180 degrees, and it takes wave L some other time difference to attain this 180 degrees, okay? So we already have a delta T, we already have a time difference here, which is, from what you see here, this is one box, okay? So you have one box, okay? Assuming that this is one box, second box, third box, fourth box, and you can complete a whole cycle using knowing the number of boxes. So let's determine how many boxes make up one cycle or one time period. All right, so we look at wave L for this. This is 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is one whole cycle of a wave. So we can see that for one time period, we have 8 boxes. However, the difference between the two waves is one box. So that gives us our answer. That's why here we have 1, which is the time difference between the both of them, divided by the total time. This gives us the fractional time difference. Fractional time difference multiplied by total angle in a circle, which is equal to 2 pi, or equivalent to 360 degrees. That gives us the phase difference. Gives us the phase difference between S and L. So we can now write in our answer that S is leading L by 45 degrees. I hope that's very clear. All right, the other part of the question is, on the graph, sketch the variation with T of X for the wavelength formed by the superposition of the two waves. Basically, what they're asking you to do is, what is the resultant wave that is going to be formed when you superpose wave L and wave S together? And of course, if you paid attention to the previous video, you could have constructive and destructive interference, and those two kinds of interferences are both kinds of superposition of waves. Now, the principle of superposition says that at a given point, you add up the displacements. okay, in order to find the resultant displacement. So let's look at this given point, or this given time. So this given time, we have at the crest of wave S, the displacement is 0.9. And at this point in wave L, the displacement is around 0.6. Okay, 0.6 plus 0.9, that gives you around 1.7. So 0.6 or 1.5, my bad. So if you add up 0.6 and 0.9, you're going to get 1.5. So the resultant displacement at this point for the new wave, or the superposed wave, is going to be 1.5. That's going to be a point here, right? And you do need to do the same for all the other points. But I mean, in order to answer this question very quickly, all you need to pay attention is look for the amplitude or the crest of the resultant wave. And the crest is going to be somewhere around here, okay? So if you look at this point, you have for wave L, I have this point is around 0.567, is around 0.7. And for wave S, it's also 0.7. So 0.7 plus 0.7, that's giving me around 1.4. So we're not even there yet. So let's try somewhere, somewhere here. Okay. So this is going to be 0.9, and this is going to be 0.8. Okay. So this 0.8, 0.9, we get 1.7. So 1.7 is somewhere here. So 1.7 is our amplitude. And this amplitude is basically a very key point in plotting this graph. So if you struggle with finding amplitude, you can just go ahead with the basic steps and just finding out what is the summation of the two of the distances and just plot whatever graph that comes out of it. So that's the key to answering this question. Once you're done, you should be able to plot a very nice looking graph that will be something like this. Okay. So in this graph, they actually have the amplitude as 1.6, right? 1.6, and that's somewhere here. So maybe I must have made a mistake in my calculation here, right? But I think you get the overall idea, and I don't think you should lose points for very small differences in of 0.1 in finding the resultant wave. Just make sure it's consistent. That's the key. Okay, so let's look at the second question that we have here. This question I had shown you guys in class. Just take a moment to read through the question. All right, so it says for the instant when t equals 2 milliseconds. So this is t equals 2 milliseconds. What is the phase difference between the waves and what is the resultant displacement of the waves? So remember how you find the phase difference. So let's look somewhere at t equals 2 milliseconds. At this point, to be honest, I find it quite difficult or not as easy to find the phase difference. So I'm gonna stick to something that makes my life easier, right? And what I want to do is I'm gonna look at any point throughout the graph to find the phase difference. Now this region looks interesting to me, okay? Because it's just easier for me to see that this graph, when it's at 0 or whatever this point is, this is at maximum. This is at 90, and this is somewhere around 270, okay, or 180, okay? So wherever this is, we can see that this is a difference of 90 degrees. And 90 degrees makes it easier for me to pick an option of D or B, okay? So that eliminates A and C. The next point is finding the resultant displacement. And based on the rule, at t equals 2 milliseconds, all we have to do is what is the displacement of this wave at this point? What is the displacement of the wave at this point? And you have to add them. Add them up, and that's the answer. So at this point, we have this wave has a displacement of positive 1, and this wave has a displacement of, if you go down, this is 1.2, 1.4, 1.6. So this is 1.6, negative 1.6, however. So negative 1.6 plus positive 1.2, and that gives you negative 0.6. That's a very quick way to answer this question. Of course, this should take you 1.5 minutes to answer, and that's all you have to do for this one.